Hello, good morning. Let's continue our previous lecture. We have discussed data association techniques and we have discussed some problems regarding data association. We shall now continue from our previous lecture. The next topic in this chapter is false alarms. These are actually false positive, or we can say these are false measurements that enters in the surveillance region. They can come from the sensor imperfection or detector failures, because as you know, when sometime what happens that target disappears in the noisy environment, like suppose the target is our drone UAV or drone which is flying in some service space, and is moving in the with cloudy environment, or is moving behind many behind some rocks or mountain or any shadow effect. So these are some uh, or or it may fly in the very foggy environment, foggy weather conditions. So it can cause some detector failures, and the detector could not find the target in the noisy environment. So they raise the two questions: what is actually inside the track validation gate? For example, this service region, and there are a few measurements in this example. Two are very far away, and two are selected in the validation gate. So, which measurements are the which measurement is a real measurement and which is a false measurement? So, this is a big question in this regard. And so the track select the both measurement, but the track do not know which one is the real and which one is a false measurement. As we discussed, the validation gate in the previous lecture. So the validation gate is actually select a subset of measurement from the surveillance region, and the surveillance region have plenty of measurements. And here, how to model the false alarms. They are uniform over the sensor space, and it is independent across time. Assume temporarily that the sensor field of view, uh, or suppose the surface area V is discretized into n discrete cells, 1 to n. In each cell, the false alarm occurs with probability Pf. Assume independence across cells. The occurrence of false alarm is a well-known process, like flipping an unfair coin with probability Pf. Then the number of false alarms, MF, or the number of false measurements follow a binomial distribution, and this is an example of binomial equation, which takes the element of n discrete cell and the number of number of false measurement, and the p MF is the probability of number of false measurement into 1 minus p whole power n minus mf, with expected value np. So, for example, this shows the when n equals to 20, and probability for the false alarm probability 0.5, and when the green dot shows when the probability 0.7, and at n equals to 20, and when probability 0.5 and n equals to 40, the red dots. So it shows uh, the process for getting the probability of the false alarm. Let the special density lambda is actually the density of the collective measurement in coordinate of x and y, with the number of false alarms over the space V. So lambda is n over v. Okay, for example, and it can be measured in meter square. So like now, n tends to infinity. That is, we reduce the cell size until the continuous case. Then the binomial becomes a Poisson distribution with this one. So, and the previously we were considered binomial process. Now we have we want to reduce cell size in the binomial process with the Poisson distribution, uh, the gamma. So it takes the exponential power of gamma into some space v into this one, and which takes the normal binomial process distribution, normal Poisson distribution at lambda equals to 10. So this is a normal Poisson distribution at lambda equals to 10. It means when we select lambda equals to 10, then it can be plotted like this black dots, and if we reduce the value below the 10 like 4 and 1, that can be also used, but for the normal distribution, we should select lambda equals to 10, and similarly, the measurement likelihood of the false alarm is assumed to be uniform like this. In case of if we want to calculate the likelihood, then it will equals to 1 upon v. The probability is 1 upon v. And if we want to calculate the likelihood of the target state, then it takes the normal Gaussian equation, like we have discussed in our previous lectures. The So these are the we have discussed the problems in the data association. Now, how to solve the data association, like single target data association? Let us consider the single target like this one. This is a single target, and a single target to track already initialized the detection probability less than 1, and false alarm probability is greater than 0. Means uh, this is due to the misperfection or the detector failures is probability greater than 0, and your track always initialize with the loop-by initialization with the updated PDF probability density function, and having the detection probability less than 0.1, for example 0.01 or 0.001, and then during the data association we maintain the probability, we update the probability based on the state estimation and the probability existence formula to update the detection probability up to 0.95, or so usually the probability you can the updated probability below the 0.95 or 0.98. So the data association approach, yeah, to approach non-Bayesian and Bayesian. So here now non-Bayesian, there is we do not know periodic information. We do not know the periodic state PDF, and in the Bayesian we know the periodic state. So that's why we use the Bayesian filter, like gamma filter, and in the non-Bayesian we use we do not calculate the association probabilities because we do not know the periodic PDF. For example, the nearest neighbor standard filter and the track splitting filter, and the Bayesian is a probability data association filter PDF is an example of the Bayesian where we calculate the association probability. So what is association probabilities? Usually when we build a validation gate, now we want to associate this uh, measurement and this measurement to this track. So But for a single target, one track has should have one measurement only. So we should calculate the association probabilities between this measurement and this track and this measurement to this track. Uh, so uh, so let's see how to do this. In the nearest neighbor standard filter, we should compute Mahalanobis distance to all measurements. Uh, if there are two measurements selected in the validation gate, then no, I'm sorry. Suppose there are many measurements 30 or 40 in the surveillance region, we should compute the Mahalanobis distance to all measurements in order to accept the closest measurement and in order to develop the validation gate. So to develop the validation gate and to accept the closest measurement, we apply some validation threshold. And if the distance is less than some threshold, some getting threshold, then those measurement will be accepted for the track update. Then update the track as it were the correct measurements. So it's like the classroom, okay, where or exam hall or the exam hall. So in the exam hall, for example, 20 students are should come for the should have to come for the exam, but due to our limited space, like if we have suppose 10 seats, then we have to select only 10 among the 20 students. So like this one. So and also if those students are selected, then the gate is open. Only those students can into the class or into the exam hall which belongs to that class. So here the problem with some probability the selected measurement is not the correct one. This so because detection probability is less than zero point 0.1, so the selected measurement is not the correct one, or maybe correct, we don't know. So this can lead to filter divergence or covariance collapse regardless of track loss. Because although the validation gate is developed using Mahalanobis distance calculated and some close measurement of the prediction are selected, but as we have very low probability of the selected measurement, so we can have these types of problem. Conservative nearest neighbor variant, it is some variant, it do not associate in case of uncertainties, that is the NNSF filter. In case of uncertainties, it means that if there are many high uncertainties, means a large number of collected measurements, then we should wait for the better conditions. It means, for example, the target is moving in very noisy movement, then it do not associate in this case. The association to the track is very difficult in the noisy environment. And the second variant is the strongest neighbor strength filter, when you have confidence measure associated with each measurement, and also it sometimes overconfident. The track filter become overconfident, the that it assure you the associated measurement uh, belongs to the measurement, means it sometimes the track the object with overconfidence, and it can lead to the wrong estimation. Single target data association. Uh, Here, uh, the Bayesian approach, single target data association (PDF) is the Bayesian approach, and it integrates all measurements in the validation gate. It means it assigns all measurements in the validation gate, conditioning the update on the association measurements. Means based on the association measurement, it integrates all measurement, and it integrates it assigns measurements to all trace that are selected in the validation gate. So suppose the theta I is the number of selected measurement, okay, is equals to ji is the correct measurement, and no, if it means 0, okay. So theta I equals to may become zki if all measurements if the zki is the correct measurement, then if the theta iki is equal to zki, and if there are no correct measurement, then the theta ik is empty set, we becomes a 0. Okay, suppose there are two measurements or correct measurements. Okay, two measurements are satisfying the distance, and their distance uh, is less than the getting threshold, and they are selected, they are correct selected, then they have the mk measurements, means two measurements are selected in this set. And suppose in the next scan there is no measurement is satisfying the threshold of the validation gate, so there is no measurement select. Suppose in the next scan the distance of all measurement are very far away, and the distance of the measurement are fall across the validation gate, so in this case we cannot create the validation gate because all measurements are not satisfying the getting threshold. So so in each scan it can happen sometime each scan can select the correct measurement, and sometimes they do not do not select the measurement, it can be empty set, okay, because of the the threshold equation fails. And then the association probabilities are calculated for the selected measurement. For example, in scan per 5, two measurements are correct measurements, then the association probability are calculated for only two measurements. And for example, in next scan number 6, there are no measurements. There is zero measurement. There is empty set, and there is no validation gate because none of the measurement satisfying the threshold. So the beta ki becomes 0, like this one, like this equation. for for a Poisson false alarm model, this becomes the association probability is equal to this one, e over b plus summation of uh, false uh, alarm density, where ei is equals to the Poisson distribution collector measure density into detection probability into getting probability into the inverse of the this part is the likelihood. So your likelihood is calculated with this VKI, as you know that this is the z minus z mean, and having the zero, this is the actually, as you know, z minus z mean, okay. So, and having the zero mean and covariance of this one, okay. So and when we divide it when we divide it with 1 upon pg, this is actually likelihood of the measurement. So the data association probability of the ith measurement is equal to the your collector measurement density, the Poisson distribution into the PDPG into the likelihood. So if suppose if there is a null set of the measurement, means there's the theta I at a scan k is empty set, has no measurement, has measurement zero measurements, then this beta association is equals to the collector measurement density into 1 minus PDPG. Okay, so that data association probability are calculated for only the selected measurement. And then the first step is initialization, then creating the validation gate, then calculating the association probability, and then the state update like this, and we can now define the combined state update. So the combined state update it means this is sum up overall an association events that is the selected measurements, and we use the beta association to sum up all state estimation, and this is a result of this one. Okay, here I is here I is actually the number of state estimation, because this is not a single state, this is here I, because this equation is in this v is equals to z minus uh, z minus xp. Okay, this is xp same, but here z has some dimension. It can be uh, mk measurements, it can have 5 measurements, 6 measurements, so we do not know. This is a sensor output, the z is a sensor output, and xp is the previous prediction. So that's why the output of Kalman filter update may be the ith state estimation. So we can sum up all state estimation using this formula and combine the state update using this formula. The beta association probability, the beta association probabilities always lie between 0.01 to 0.99. As you know, the probability is always 1, and is always in between the 0 and 1. So the events theta ki which are selected by the validation gate are assumed to be exhaustive, that is they sum to 1. It means uh, when we sum up all uh, when we sum up all, then it will becomes it should be equals to 1. Okay, the events are assumed to be exhaustive, that is they sum to 1, and exclusive, that is they cannot occur at the same time. So, and similarly covariance, this is a common filter output, and with the probability beta o, it means none of the measurements are correct, so there should be no update. If there is no update, then beta equals to beta 0 equals to uh, this equation, beta 0 equals to this equation. If there is no measurement, then there is the false measurement into 1 minus BTPG. So this is the measurement 0, as association probability is the false measurement, and with probability 1 minus beta, the correct measurements are available, and the posterior covariance is updated like this one, like this one. If there are measurements, then we should update the posterior covariance with this equation. Since we do not know which measurement is correct, so we spread the innovation across all measurements in the validation kit like this one. So here our covariance uh, is will become the sum of we should have sum of all covariances with the beta association, and this we should add this thing and this thing. So in this way, we can spread the innovation across the all measurement and the validation period, because we do not know which measurement is correct. So this has effect of increasing the uncertainty of the filter when multiply measurements with when multiple measurements fall within the validation period. Then summary: nearest neighbor strength filter is, it is simple to implement. Can integrate the wrong measurements, false alarms, and thus produce overconfident estimates. Good if prediction and measurement models are accurate and price cycles are fast with respect to target dynamics. Good if data association uncertainty is low. There are uncertainty measurements are very low. And in case of probability data association filter, this is a bit more involved to implement. It means there are some more equation to involve, like we should have to calculate the association probability, and then apply it to state update, and we should combine the state update with the beta association probabilities, and also for the covariance update we should spread the covariance of all measurements in the validation kit. So this is a little bit more involved to implement the equations, and the PDF can significantly improve the tracking in region of high collector, where NMSF could not work in the high collector. It can work only in the low collector, and so the PDF can track in regions of high collector densities where NMSF becomes unreliable because of its high probability of track loss, and it is a suboptimal method, never totally correct and never completely wrong. Uh, in case of multiple target, there are multiple association. In case of single target, there should be single association of the measurements in the track, but in the multiple target, there are multiple measurement association. So here tracks are initialized, and detection probability is always less than one, and the false alarm probability greater than zero. So for example, the two tracks are initialized, and both track build their validation gate like this one and this one. And as you can see, the this measurement lie in both validation gate, this one and this one. So this measurement and this measurement are shared between the track 1 and track 2. So there's always a miscorrelation, because the track 1 can can say that this measurement belongs to me, and track 2 can say, no, this is my measurement, I am following this measurement. So they can uh, collapse because miscorrelation. And sometimes if track 2 is following this measurement, then track 1 can push the measurement this one to track 1, or they can, if the track 1 can steal the measurement from the track number 2, and switch it's always try to switch the measurement in the two tracks, or in the multiple tracks. So Uh, Whereas this measurement it totally belongs to the track 2, but only this one and this one is two measurements are assigned or is lie in the validation gate of track 1 and track 2. So these always miscorrelation in the measurement. So they generate then it generate a lot of complexities with the association probability. So there are two approaches: a non-Bayesian approach and the Bayesian approach. In the non-Bayesian, the nearest neighbor standard filter and interpretation tree, joint mobility, and the Bayesian approach, the joint PDF. Joint PDF similar to the PDF filter like in previous one, but when we talk about the joint means the shared. Joint with the shared. When we when we add the joint, it means we talk about multiple target tracking. And in multiple hypothesis tracker, this is also example of the multiple target because it generated multiple hypotheses for the target, and also the multicolor Markov chain MC data association. So there are many approaches, but we will discuss only few in this class. And also in this course, you will study only single target tracking. And this lecture is just introduction to multi-target, but we only focus on the single target tracking in the next classes. So in the multi-target data association, for example, this is the matrix Dij. So Dij is the is used for this validation gate. This equation actually generate the Mahalanobis distance equation in the matrix form, because we have a lot of measurements, some from target 1, some from target 2, some from target 3, and so it can generate the matrix like this one. And we do not know the which measurements lie in the validation gate and which is outside the validation gate. So we should calculate the distance of all measurements. So this is, as you know, the z minus z or xp. So how to iterate? Actually find the minimum cost assignment in A. Remove the row and column of date assignment, and date assignment is selected for the validation gate. Check if assignment or in the validation gate. Unassociated tracks can be used for track deletion. Means suppose uh, few few measurements could not associate because they are far away from validation gate, or they lie on outside the validation gate. And some unassociated measurement can be used for the track creation. Means some unassociated are in the validation gate, but they are newly initialized. They are newly initialized. So we should calculate the association probabilities only, not unassociated. So we can avoid unassociated tracks for the track deletion, and unassociated measurement can be used for the track creation for the new track uh, measurement, because if it is far away, then it can be lie in the next scan. When we go for the next scan, it can be selected in the validation gate of the next scan. But for the current scan, we can remove, because the current scan, they are far away in the validation gate. So here, generally it does not find the global minimum, the greedy algorithm. You can look at the greedy algorithm on the internet. So the conservative uh, uh, and variant that no association in case of high uncertainties. So it can work on low uncertainties, but if there is high uncertainties, then it is difficult to associate the measurements. So in case of global NNSF, this NNSF we calculate this uh, like validation equation like this one. But in case of global NNSF, there are two methods: assignment methods, and other one is the uh, interpretation tree. So in the assignment matrix, you have to build the matrix assignment like the previous one, like this one, and now solve the linear assignment problem with this one. So here you should select the minimum cost function of the distance like this one. So you have to find the global cost minimum. There are two methods: the Hungarian method and the Munkeris method. The first one is a square association matrix, and Muncri's algorithm is used for the rectangular association matrices. Okay, so once the association matrices are created, then you have to check the assignment or in the validation gate or not. Then perform the data association jointly and find the global optimum. This is the rectangular assignment, and this is the square assignment. And suppose in the square assignment all are false measurements. So this is the false measurements are the PF, and the distance are entries of this one. The D is the entries of this one. So suppose in the surface region there are two tracks, T1 and T2, and there are measurements like Z1 up to Z8. Okay, so we should calculate the distance between each measurement, Z1, Z4, Z3, Z2, and Z7 to everyone, and but only Z4, Z3, Z5, and Z6 are selected in track 1 and track 2. And here Z5 and Z6 are shared or joined in both validation gate. And you have to note that each track individually and separately calculate the validation gate. First, the track one calculate the validation gate like this one, and then it's separately, and then track two. Then in the next iteration, the track two is initialize and form a validation gate like this one. But unfortunately, the track two select the same measurement that was selected by the track one. So here the matrices are generated with for these measurements, and and all and the association probabilities are calculated for all of these measurements. Suppose this is whatever, this is very complex because this is very large matrix, very large matrix. It is also very large matrix. So association probabilities are calculated for every entry. In case of interpretation tree, a solution of GNN is in presence of constraint. It was introduced in the 87, and it was used in feature-based SLAM the simultaneous localization and mapping. You maybe already know by SLAM. It is used to map the position of, and it is used for to generate the map, and it is used for to localize the position of the vehicle in the map. The main idea consider all possible association among the measurements and the tracks. The association are built over the tree representation. A depth first visit on the tree is performed and constraints are used to prune the tree. Worst case is exponential complexity. The whole number of association means if you want to calculate the number of association, the number of association is equal to number of tracks plus 1 uh, power number of measurements. For example, there are 8 measurements and there are 2 tracks. Then number of then number of association is 2 plus 1 and 8. So it is 3 power 8 and it's whatever the value. It is I think mm, 6,000 is equal to 6,561. This is equal to 6,561. So this is very complex exponential. It's very complex. Its complexity is increases exponentially with the number of measurements and number of tracks. As the number of measurements and number of tracks increases, the complexity increases because the matrix, the size of matrix increases like this one and more because uh, it's set it's set like uh, um, binomial distribution like it map z1 to this one and this one and then z5 and this one so it just map all association to the tracks and calculate the association probabilities of every measurements of every entry. So uh, and other thing the interpretation tree like this for example this is validation gate and few measurements or the g is a cost function. The few measurements are g is a measurements the few measurements are outside the validation gate and few measurements inside the validation gate and the L is the track and suppose in the track 1 there are 8 measurements and these measurement has first we have to calculate the cost function and suppose the minimum cost function of the measurement is g3 and so g3 will create another L measurements in the track number 2 and suppose we have to calculate again cost function in the track number 2 and suppose g7 has a minimum cost function and then similarly uh, g7 create another 8 measurements and among them the minimum cost function is g2 so we can select the subset like this one L1 has a cost function g3 minimum and L2 have a minimum cost function g7 and L3 has a minimum cost function g2 so this is like a tree so and in this way, we can calculate the global nearest neighbor filter. This is another example, and this is another example. Like suppose the target is maneuvering like this one. So the black dot is the collector, and the circle or the prediction, and the target is moving up to here. So at this point, after this point, we do not know the target will move up up this sphere or this side. Okay, so here suppose two tracks are generated, and one track is create the validation gate here, and other track is create the validation gate here. But uh, the the measurement prediction, uh, same measurement prediction lie in this validation gate and this validation gate. So still the track one can can say that this is my measurement and give me back, and they can fight, they can fight, and they can make an argument like this is my measurement, this is my measurement. So this is, so due to this there can be miscorrelation, and both track can be lost, or one of the track can be deleted, and other track can follow the measurement prediction. So comparison, assignment solver is a fast polynomial, and interpretation tree is a general constraint, and in the assignment libraries available, and miscorrelation, and interpretation tree, general constant, extensive search, find appropriate assignment, and but it has cons like it is slow, exponential, complexity, and the assignment is uh, only linear constraint, blow of cost matrix means blow means the cost function is very expensive, cost matrix is very expensive. So interpretation tree are good when several constraints are available. In other case, assignment solver are preferable. In case of joint compatibility, uh, so there is comparison. Individual compatibility like a single target. Uh, there are in this measurement independent tracks. For the independent tracks, so for example, the single target, one measurement integrates includes only one track, like in the single target tracking. One measurement per track assumption, typical of target tracking. And the joint means correlated tracks. One measurement integrates influences several tracks. Means one measurement assigned to several tracks. And multiple measurement per track association, typical of localization and slam. So this is example of localization and slam. For example, in the mapping, there are many objects, and the track can have many similar similar measurements. So don't worry, we will not go through in detail. We it was just this is introduction of the multiple target. So like you know the this is the measurement equation. This is same as we have discussed. So here H is have this matrix because we are talking about the joint measurement equation. So the joint measurement function here is HF is equal to this one, and the hypothesis is jointly compatible if and also don't be confused with this equation. This equation is same as we have discussed in the previous slide, like this one. This is same as this equation. So the z is this equation is view, and the covariance is this one and also this one, and this some threshold chi-square distribution threshold or getting threshold. So this is Mahalanobis distance. If this distance less than this one, the joint measurement selected, or the joint measurement association probabilities. Now the joint probability data association, it is very similar to the PDF, um, and is a natural extension of PDF filter. It assumes the number of established targets among the collector known. Measurements from one target can fall in the validation gate of a neighboring target. This situation can happen over several sampling times, means it can be happen in each scan and acts as a persistent interference. This is summarized by an approximate sufficient statistic consisting of state estimates which are given by approximate conditional mean along with the covariance of each target, like in Kalman filter or other Bayesian filter and Markovian filter. So the states are assumed to be Gaussian distributed with means and covariance according to approximate sufficient statistics Kalman filter. So the method is very similar like you have done in the Kalman filter. So PDF is similar to the Kalman filter, but when we talk about if we want to involve the data association in the Kalman filter, we just include the validation gate. Using the validation gate, we select some selected measurement, or we select a subset of the measurement of the sensor, and then we assign the those measurements which are selected in the validation gate to the tracks, and then finally calculate the association probabilities, and then apply the Kalman filter for the track output. The PDF models all incorrect measurements as random interferences with uniform spatial distribution. The performance of PDF degrades significantly when neighboring target gives rise give rise to persistent interferences. So PDF consists of following step. First one, in measurement to target association probabilities are computed jointly across the target, like multi-target NNSF. But now it has the periods like Bayes formula. In the NNSF, we do not have a periodic PDF, but now in case of Bayesian, we include the periodic PDF, and the association probabilities are computed jointly across the each measurement prediction and each selected measurement prediction, and association probabilities are computed only for the latest set of measurement. It means the beta association probabilities are computed for only current scan measurement, like ZK. So ZK use the association probabilities are calculated based on current measurement. The state estimation is done either separately for each target, as in PDF. So, like in PDF, we can calculate this separately. We call this decoupled state estimation, or in a coupled manner using a stack state vector, resulting in a JPDACF coupled state estimation. The key feature of the JPDF PDAF is modeling of this one, where uh, this element is the event at measurement J originating from the track T J at time K. Finally, the MAST, and here uh, we just try to understand the how the joint association, how the joint hypothesis is created. So multiple hypothesis tracker. In this part of the lecture, we just study about how the multiple hypotheses are created. MST reason about it is a reason about the association of sequence measurement with tracks and false alarm. It associate the sequence of measurements with tracks. It interprets interpretation of the measurements as false alarms or new tracks. It means it always get confused or always try to interpret which measurement or false alarm or which measurement or the new tracks and the interpretation of tracks or is updated or deleted. It is updated or should be deleted. Evaluate the probability of the association hypothesis and optimal Bayesian solution. So here the procedure for the algorithm: initialization, state and measurement prediction, hypothesis generation. In the next slide, we will talk about the hypothesis generation and hypothesis probability evaluation, state update, and hypothesis management, pruning, elimination, and creation. But for your simplicity, we will not discuss about the equation. We just talk about in the theoretical and in the figure form, and exponential complexity of the full solution. So to decrease the complexity of the solution, we apply the pruning and k-best hypothesis. So both strategies delete the number of hypotheses so that we can reduce the complexity. Okay, suppose uh, this is a set of hypotheses. Theta is a set of hypotheses, measurement prediction, and all other collected prediction at time k is a history of assignment set theta, where theta is observation and theta tracks. So theta and up to time k. So theta observation may be the sensor observation z1 to zm, having the cardinality mk measurements in the observation set is a set of measurement association where measurement is either associated to track. Zi may be valid track, may satisfy the validation get equation, and so may be assigned to track t, or it can be created as a new track zi equals to n, where n shows the new track, and or a false alarm zi may be false. So you have to note this notation t. T means this equation means the validation, the measurement are certified in the validation get, so and it is assigned to track t, or it may be treated as a new track n. If zi is n, it means the track is newly initialized. If zi equals to f, it means it is a false measurement. And the theta track, there are L1, L2, L3, and LT tracks, where T is the number of tracks. The set of track label where track can be matched, like this one M, like a measurement. It can have some measurement like MK measurement, or oculated. We can oculated the measurement. Oculated means uh, in very narrow route and very narrow space, uh, and few in narrow space, few track can be uploaded, means the track can be missed out, because in narrow space only few track can be passed through the narrow space, but we can not but not all the tracks can pass through the uploaded region. And the deleted li could be deleted because of low detection probability, or maybe a false measurement. It can be deleted, or it can be uploaded, or it can be matched in the validation get, so it have a m measurement. And second thing, hypotheses are generated recursively in a tree-based structure. Okay, so it can uh, unlikely branch unlikely branch are avoided by validation gate. Those branch of tree which are unlikely can be avoided or deleted. And exponential growth of tree, each scan has means each branch can have a another tree, can generate another branch of tree, and that branch of tree can create another branch of tree. So like tree in the garden, like tree of in the garden, you can see a very large tree, and every tree has a different uh, route or path, and only subset of hypotheses are generated in practice. So like this one, so let's see in the practical. For example, there are two tracks, track 1 and track 2, and track 2 has validation gate, and track 1 has a validation gate. This one, but you have to note that Z1 measurement is associated to the validation gate of track 1 and to the validation gate of track 2, but Z2 is outside the validation gate. So there is no association of Z2 to track 1 or track 1 or track 2. Okay, there is no association of Z2, but Z1 is jointly shared between the track 1 and track 2. So for example, the theta predicted state have three four possibility, four hypotheses, one, two, three, four hypotheses. So considering Z1, so Z1 could assign track 1, Z1 could be assigned to track 2. Still we are confused. Still the algorithm is confused because both track 1 and track 2 have a same measurement Z1. And other hypothesis, the Z1 is a newly initialized track, and other hypothesis is Z1 could be a false measurement. Okay, so considering the Z2, another hypothesis Z2 is a false measurement, and Z2 could be a new initialized track, and all have same because Z2 is outside the validation gate. It means the Mahalanobis distance of Z2 to track 2 and track 1 is very far, so it's not selected in the validation gate. So in this hypothesis, each hypothesis have hypotheses. Each hypothesis generate two hypotheses. First one is Z2 is false measurement, and Z2 is newly initialized. And here also false and newly initialized. Here is also false and newly initialized. Here also false and newly initialized. Another interpretation of a hypothesis, considering track 1. Here, the first one, the first hypothesis, this first hypothesis, the track 1 has measurement. Like this one, track 1 validation gate is lie in the validation gate. So Z1 is lie validation gate. So M measurement is assigned to track 1, M measurement assigned to track 1. And here the track delete, we should delete. For example, if measurement lie in the validation gate of track 2, and if for example if the measurements lie in the track 1 validation gate, then we should delete the track 2. Then why track 2 is following the same measurement, we should delete. So here track 1 uh, is deleted in this hypothesis, and uh, if Z1 belongs to track 2, then track 1 should be deleted. And in this case, if in this hypothesis, if Z1 belongs to track 1, then measurement is assigned to track 1. But in this case, if Z1 belongs to track number 2, then track number 1 should be deleted, or track number 1 should be uh, operated. So this hypothesis have two more hypotheses like D and O. And this hypothesis, if Z2 is newly initialized, then this have two more hypotheses like occluded and deletion. And similarly, in this case, the correct one should be deleted or occluded, correct one should be deleted or occluded. And similarly, uh, this this hypothesis will create two more hypotheses, and similarly it will create more hypothesis deletion and occluded. And similarly, when we consider to track 2, then track 2 as deletion occluded. In every step, it will create two more hypotheses. And here you can see each hypothesis have a D and occluded deletion and occluded. Okay, because we can see here the hypothesis making the tree, first tree, considering the Z1 belongs to track 1, it may be track 2, or it may be new initialized, or it may be false measurement. Then what is the hypothesis of the false measurement? Either is a false measurement or it is a new initialized. And what is hypothesis of the new initialized hypothesis? It will have two more hypotheses, and every time hypothesis tree is developed. So approximation, we need to approximate this tree, this hypothesis. So tracks can be partitioned in cluster based on getting a separate trees grow for each cluster. K-best hypothesis tree directly generate the K-best hypothesis, means the best match. K-best means the matched. Generation and evaluation are integrated in a single step. Use multi-algorithm and a linear assignment solver. What is mean by pruning? Pruning means these algorithms check the pruning after n scan. For example, n equals to most algorithm use the value of n equals to 4. Means after every 4 scan, they check uh, if their probability or less than some pruning threshold, then those measurements are deleted, and those hypotheses are deleted where the probability are less than the pruning threshold. The pruning threshold uh, is maybe zero point 0.1 or zero point 0.5, or it lie between in this value. So if the probability of the association probability is less than this value or this value, then those values are deleted. If we increase the pruning threshold, then the step estimation degrades, because suppose if association probability, we want the higher association probabilities, zero point 0.9 or zero point 0.7 or zero point 0.8. But if we pruning threshold, if we increase the pruning threshold up to zero point 0.9, then all association events can be deleted. So we should limit to this value 0.1. So if those values association probability less than 0.1, they can be deleted after every 4 scan. And it keep only the most probable branch. So in this way, uh, the growth of the tree can be reduced. Suppose this hypothesis has point 0.001, and it is less than the pruning threshold, so it can be deleted. So in this way, this whole growth is reduced. This whole the tree is reduced. So this is MST example. I'm tracking of two uh, target which is crossing like this one, and this is hypothesis tree in each scan. And in detail, for example, this has a four hypothesis, then every hypothesis create more hypotheses like this one. So after every four scan, when we go down, we can apply the pruning, so we can delete few of the few of the branch, so that we can reduce our calculation complexity. So finally, we should conclude our lecture by having a summary. Nearest neighbor filter like this one, it's simple to implement and good. It is good if tracks are well separated and not noisy. Global NNSF finds globally optimal assignment solution, combining both no integration over time, interpretation tree more involved to implement good in case of general constraint among association. And JPDF is a natural extension of PDF, models the joint likelihood of measurements being generated from particular targets. It's like a multi-target and an asset, but it has a period PDF. MHT is fully Bayesian, most general framework of multiple target, complex and expensive, only approximation or practically implemented. So this is the end of the lecture, and uh, I will take next class in the classroom. Okay, good day. Have a good day.